Okay, thanks a lot. Pleasure for me to be here. This is a presentation on Frequencycomb that we designed for FOKUS to do a microgravity experiment. We are not a space company, we are a laser company, but this was the first time for us to really get in touch with space experiments, and I tell you, it was a lot of fun, a lot of effort, and we learned a lot of things, and it was a great experience. What you see here is the photo of this launch of the rocket from Kiruna. I'll come back to that later. The project itself was called FOKUS. It's an abbreviation for Frequency Optical Comb under Schwerelosigkeit. Schwerelosigkeit means zero gravity. This project and experiment I will just mention, then talk about the architecture of this comb and the technologies that we use there, then our experiment on two rockets. The first one was Texus 51 last year in April 23rd, and the second one just launched in January this year with a slightly modified experiment. Both experiments very successful, and then I talk shortly on future applications of such combs for space. Okay, and get the FOKUS team. So a frequency comb, as you know, if you want to make the accurate clocks, optical clocks, and then want to bring them down in frequency to the microwave range, you need an optical comb, and therefore the goal is on the long run for us to bring these frequency combs really to use for the space community. It's more or less a chicken-egg problem. Some problems like mentioned in LISA and so on could maybe be solved, so laser stability and so on could be solved very easily using a comb, but the comb is not ready yet for space. It doesn't have any heritage, and we are working to get towards this heritage. So the goal was first to develop a frequency comb for use under microgravity on a sounding rocket, so that it survives the flight, that it works and operates remotely controlled. The work packages are make a robust, compact, automated comb, design, mechanics, electronics, and software, and then we combined it in Texas 51 with a Rubidium spectroscopy unit developed by our partners, and worked on the interface with the Texas rocket to ground control, so that we can operate it from ground control equipment. And on the second slide, we extended this concept, added another externally controlled potassium spectroscopy module, connected that with fiber to the comb, and improved also the log scheme for the Rubidium. So what you see here is a glance of the module. This is not, maybe does not look like a nice space-proven clock, a cesium clock, as we saw in the first lectures, but the major things are wirings outside, which we of course had to bring outside of these box. That can be made more nicely, of course, on the long run. What's the experiment? What we did? In principle, we do a clock comparison. We have a Rubidium optical reference locked to a 384 terahertz transition. We beat this line with the nearest comb line, which gives us some 61 megahertz signal, and compare that with the cesium reference. That's a commercial reference from Microsemi. And so we have a clock comparison from the 10 megahertz radio frequency range to the 384 terahertz. The clock itself, the optical module is about this size. It's 145 millimeter by 220 millimeter, 30 millimeter high. large height. It has some free space optics regions in there which are needed for the F2 interferometer. This is a polarity cooled lithium narbide crystal, a waveguide crystal for frequency doubling of the center frequency of the red wavelength part of the comb, and make the F2 interferometer. And then we have a frequency doubling unit, also a pipeline producing the 780 nanometer for comparison with the rubidium. And then we have a small free space part here which is needed to control the length of the comb, and where we do some polarization tricks. The whole thing has a 100 megahertz repetition rate. Output power of the oscillator, 3 milliwatt of the amplifier is about here is about 150 milliwatt. The spectral bandwidth is 39 nanometer. Startup time of this oscillator is less than 10 seconds. It's a turnkey oscillator. You switch it on and it locks, mode locks, and then it's vibrationally robust to 8 to 9 G RMS. And we used it we checked that on a shaker between 50 hertz and 2 kilohertz was the white noise shaking. The basic technology of the oscillator is what we use also in our newer comms at Menlo Systems. It's what we call figure 9 comb oscillator. It's a non-linear amplifying mirror oscillator, which has the doped fiber in here. We have some phase shifter, an output coupler here. We pump in the light here, and here we have our free space optics where we have actors for the offset frequency and for the ref rate. So it's a very simple laser in principle, can be made very small, and is very reproducibly to build. And if you use the right actors here, so fast electro-optical modulators, you can get extremely low in phase noise, and you can get very stable. Please check out our poster on number 143, where we show a comb comparison, which starts here at 10 to the minus 16 at 1 second and go down to the below the 10 to the minus 18 regime in 1000 seconds. This is good enough for the best optical clocks that are on the market, in the labs available for the moment. So for this rocket comb, we did not use so fast actors because fast actors needs more complicated electronics, eats up more energy, makes the whole thing a bit more complicated. Already developed as a technology in 2009 was the fiber butt coupled lithium niobate F2 interferometer unit, more or less a waveguide here where we butt couple the fiber in and get the frequency doubled light. This gives us an offset beat node in the order of 40 dB at 1 megahertz resolution bandwidth. So this is way enough to lock the laser securely to a nice offset beat. What we also checked in the earlier years was radiation degradation of some doped fibers. There's still some way to go here, but the bottom message is, these fibers degrade. We lose transmission over the course if we irradiate this with one kilogray or so. The good news is that this degradation heals. These color centers are very weakly bound. You can anneal them even at room temperature, or they go down. If you heat it up to 180 centigrade or so, it goes relatively quickly down, and there's good chance that we find a combination of a specially designed fiber and annealing processes to really have solved that degradation problem. And as far as I know, there are already some radiation-hard fibers, iridium-doped fibers on the market, maybe not as highly doped as we need for our oscillators. But we will look into that in the course of the next 2 years. So there's a paper on this comparing different fibers. The Rubidium spectroscopy unit was built by collaboration between the University of Hamburg and Ferdinand Braun Institute in Berlin, in combination also with the Humboldt University in Berlin. The one part, the Ferdinand Braun Institute designed this very small and robust distributed feedback laser. This is on an aluminum nitride platform. This laser is precision current controlled by a specialized electronics that we made, and this is stored into this spectroscopy cell, which is built on a zero-dual platform. Here is actually the rubidium in there. So it's a very compact, about 8 centimeter by 4 centimeter platform with the technology that the mirrors here are actually fixed, and this laser, this cell and this laser, they're very robust against vibrations and degradation by temperature. Power is about 7 milliwatts from the DFB laser. Line width is 1 megahertz, which is of course not great, but for our purpose it was good enough to demonstrate all the locking schemes. So this is a spectrum. When we scan the current of the DFB laser, we see an absorption here. We can of course, with modulation spectroscopy, get a demodulated signal here, and that actually here is the transition where we lock to, and this is which we drive with our electronics. The whole system is then assembled on a platform in a dome. This is this platform, which also is used as a heat sink for the laser. We have pump diodes below here, then we have the Frequencycomb trayer, then we have the rubidium spectroscopy, and that's more or less these 3 modules make up the optical part, and then we have an electronics circuitry up here with several models that we can exchange, and for testing we have DC converters, and we have a small onboard PC to control the unit. Below that there's a casing provided by Airbus, at that time first called Aston, then Airbus. This is giving us the connection to the rocket service module, and works for the transmission of the data. This is the module once more. We have cooling water chilling this platform here to the right temperature before start. Then during the start, during flight, this platform of course heats up. The whole comb dissipates about 60 watts of thermal energy altogether, and this is connected to the service module with 2 Amphenol connectors. And this is a small Windows PC taking care of the high-level data operations. When we put the whole thing together, then it's like that, and then we put a dome on top of it, because the free space optics part, of course, would otherwise change, because the pressure during flight changes, and we could not compensate for such such rapid changes during start to destabilize the laser. Okay, this is the automated lock of the DFB laser. What we actually do is that we first lock the laser here to the error signal generated between these two set of lines. This is a relatively smooth lock with an accuracy of about 80 megahertz or so, and from that we make a current jump that we test, of course, before the flight. We make a current jump to this transition, and the success rate is about 80%, that we end up in the right transition here, and that we see a counted signal that corresponds to the line that we are looking for. So this requires, of course, an ultra-stable and computer-controlled current supply. The current stability is in the microamp region. So the line stability, if we have locked the laser, we of course made long tests of this laser for something like 40,000 seconds. This is one typical set. You see that this set is oscillating. There's several reasons for that. One is we are using a very small clock, which is of course not of the quality of a GPS clock. It's about 1-2 orders of magnitude worse, or even 3 orders of magnitude worse, but it's a good clock, it's a good reference, good for our purpose. Starts here at about 10 to the minus 10 and goes down to the 10 to the minus 11, and then the Allen deviation of course goes up again because we have these oscillations in here which come on one part maybe from this clock. On the other part there's also some indications of etalon effects in the Rubidium spectroscopy. So we did our launch, and where did we do that? This was in north of Sweden. There's an area there which is not very densely populated, only some reindeers are living there, and this is an area where the Swedish Space Corporation, in collaboration with DLR and other European space collaborations, space agencies, operates this launch site. It's also a satellite survey site, and we are shooting into the region. It's a purely ballistic flight. It's not controlled, so there must be taken care that the ballistic is okay, which actually made problems. It caused more than nearly 2 years of delay, because shortly before our flight, the launch site realized that there's something wrong with the launcher, there's something wrong with the rocket, and so they had to work on that. The flight went up to 258 kilometers. We had about 330 seconds of micro G, and this is a typical, this is the trajectory that we calculate when we put this data into Google Earth, just to give a perspective how far out we go. There's actually nice films from the camera of the rocket, but too long to show here. Well, of course, you can do a clock comparison. If you do a clock comparison experiment, you might think about, this is local position invariance relevant. We, of course, check for this. If we compare these two clocks in change of frequency compared to the change in the gravitational potential that we induce during the rocket flight, we get a delta beta factor of about 0.2 on Earth. The best measurement is 10 to the minus 6, so we are 5 orders of magnitude way worse than that. But that measurement on Earth was over 7 years, taking into account the gravitational change in potential that the Earth experienced in the Sun. elliptical orbit. Here we have only factor 1,000 smaller change in gravitational potential and much smaller flight duration, so in principle this would improve much more if we go for a larger trajectory and if we take a better reference. So, for example, if we use the Faraday clock instead of the GPS clock, then we would be on a trajectory going towards Mercury and back. We would be able to evaluate beta to 10 to the minus 9 on such a trajectory. Second flight, wonderful day in January, coming out of the mist here, and we have this potassium and the rubidium spectroscopy. We had a better cesium reference in there, about 1 order of magnitude better. We had a locked gene scheme for rubidium changed to modulation transfer spectroscopy, and we have this K-line spectroscopy. So all these modifications had to be done under high pressure within 6 months, because we had to got the module back in May last year and had to deliver it in November for shipment to Kiruna. So high pressure. That's so to say first glance to the flight data. What we see here is that the rubidium is quite nice. Of course, during launch, there's no useful counting possible, and during re-entry also, because we switch off the lock of the comb in that period. Before that, it's flat line. Then we see that here the rubidium starts wiggling. This is the typical echelon sign that we see here. Maybe if we can correct and compensate for that numerically, we have to see. For the potassium lock, it's a bit worse, because we have here some test in between where the relocking of the potassium was tested with different strategies, so we don't get a consistent data set of the whole micro-G flight. But anyway, all 3 units worked, and we are very satisfied with the data. So once more, coming back to the purpose of all this, why are we going for frequency combs for space? What are typical applications that we imagine here, and which are also partly discussed here in the conference? One is, of course, the frequency comb is the gear to translate from the optical frequency domain to the radio frequency domain. So it's very useful for optical atomic clocks. There's no clock without the clock work. And when you have these clocks, you can of course do tricks like was in Stikvest imagined, check for Einstein's equivalence principle on a trajectory of a satellite, very eccentric trajectory that measures time, compares time between clocks on Earth and on the satellite. Of course, then you need links. For links, you can use frequency combs, as Newberry Group has demonstrated down to the femtosecond precision. That's also useful for global navigation systems, of course. And clocks can also be used to measure gravitational potential using, for example, BECs. For BECs, the clocks can be used to stabilize the lasers and control the laser frequency very carefully. We have another project with the DLR on atmospheric trace gas detection using a LiDAR, stabilizing a LiDAR for CO2 absorption, for CO2 differential absorption LiDAR. It is necessary to know your laser line with very high precision, so in the order of 30 kilohertz or so, and the clock is a perfect instrument to do that. And then we, of course, are looking into also another project here. This is there was a project formerly called Darwin, where we have where the science community was thinking about a mid-infrared telescope in a formation flight in the Lagrange point, and for detecting exoplanets that contain oxygen in the atmosphere. And such a mid-infrared telescope would require the distance between the telescopes with very high precision. And that was the reason why Darwin actually was cancelled, and the DLR has invited us to look deeper into this problem and look for ranging strategies and formation flight strategies together with other university partners. And based on comms, we are currently working on that. Okay, and with this, I'm at the end of my talk. The team was pretty large, initiated by Hänsch and Ted Hänsch and Ronald Holzwarth. Was this FOKUS project. We actually closely to the point where I joined Menlo Systems, and together with Tobias Wilken, we set up this first Kamm, and Christian Deutsch and Michele Giunta, and we're working on the experimental setup with us, and Olaf Mandl made the software. There's a big group from the Ferdinand Braun Institute by Vladimir Schkolnik, Kohfeldt, Achim Peters, Markus Krutzik, working on the Rubidium spectroscopy, or more or less on the DFB laser part of the Rubidium spectroscopy, and then we have the University of Hamburg with in the Sengstock group with Hannes Duncker and Hellmig helping us to set up the Optical module for the Rubidium spectroscopy. Okay, thank you. And last but not least, of course, I thank the DLR for generous funding over many projects during the